And we're back with some more oxygen not included. And today it's all about putting together a sour gas boiler. Not a mini sour gas boiler, not a mic. It's like a medium sour gas boiler. Medium sour, let's just say. Down here, I'm thinking we're going to need to have the start about there, and then we're going to need to go in about 51 tiles. Ooh, so about there-ish. Give me a minute while I excavate this out. Normally about now I would be, well, either vacuuming this place out or doing something along those lines, but unfortunately we have an unknown tile. So we need to melt this, and then we need to have a duplicate drop through it. So I'm thinking temperature shift plate behind it, a bunch of hot water on top. Actually, not hot water's almost. We'll melt this, and then we'll drop a duplicate through it. It should be fairly quick. Well, the melting should start, but I can't actually tell what temperature that ice is, though it doesn't seem to be doing any weird wiggling. The salt water here is hot, if there's any, or hot enough. If it's not, we've got plenty more down here. We're also moving all of this ethanol out of the way. We want to turn this entire area into a little sour gas boiler. Thing is, we're integrating the power supply. Hey, there we go, finally done. The reason I'm saying that is, well, that's why it's so large. The actual sour gas boiler itself is going to be not as big as the power generation area, which is going to fit over here. So, let's just block off this area and vacuum it out first. And now that we've got a duplicate trapped above it, we should be able to have them fall right through that tile. And excellent. Now we can build there. Otherwise, that would just be an annoyance. All right. Let's brick this sucker in, seal it up, and then vacuum the whole thing out. We're going to start with a vacuum. It's just going to make it easier to build what we're trying to build. We could have also... I was tempted to just basically brick this entire place up, but I think that might actually take longer. It's just more time consuming. It's easier to just stick in about 10 vacuum or 10 pumps and just vacuum the whole place out real quick. Before we've even vacuumed this place out, we're going to start on, well, the construction, because this is going to be a long project. Now, over here, we want to fill this up. We don't want to put in 1,000 kilos of water on each tile. We've got 4 tiles, but what we want is about 950 kilos. If you go too high, you start encountering some problems. We're going to be putting a door on top of this, and it causes weird liquid physics. So 950 per tile. So we've got this set to is 475. 475 and 475 is 950. So this will give us 2 tiles worth of 950, and then we just reset them and do it a second time. This makes sure that I don't accidentally let this fill up too much, because I'm terrible for just forgetting about things. And then when I look back, it's like, oh, it's overflowing, and I've messed stuff up. Happens far too frequently. Oh, I should pump this stuff out of here when I get a chance, though. I think currently, one of our liquid pipes is currently occupied. You know what? I'll pump this stuff out later. For now, we're going to finish vacuuming this place out and maybe do a little bit of prep work if we can. And there we have a perfect 950 kgs in each tile. I mean, it's not necessary to be exactly 950 kgs, but the fact that we can do it so accurately without messing up, very rare for me. Very, very rare. All right, let's... there's a whole bunch of random piping here. Don't worry, this will all... Actually, I can't promise it's all going to make sense. It'll... You know what? I'll figure out a way to make this make sense one way or the other. It does have logic and reason behind most of it. It's just... It's not obvious most of the time. We are just about... How did a building melt? Damn it! Oh, a rocket. Oh, this rocket is melting a lot of stuff. I'm gonna have to go back there and fix that. But for now, this over here, we've got so much in place. Yeah, there's the automation. There's the gas piping. There's the liquids. They're actually quite, reasonable. There's some things going on here. Even the shipping rails aren't that bad. Though I should probably expend on those conveyor rails just a little bit. There's some stuff we can do with that later. Now, right now, I'm pressurizing this area with hydrogen gas. I need about 20 kilos of hydrogen gas pressure in here, in this room, and, well, the steam turbine might as well get it as well. And I figure we can do all 3 of them in this one area, so why not? And we're using a liquid lock to make sure that none of the gases escape. The rest of this place is all vacuum, including this area in here, which is sealed off by a visco gel lock. So, give me a few minutes while this fills up with hydrogen. To prime the system, we just stuck down a little liquid pump there, and we dumped off some supercoolant to get into this and this. We don't really need supercoolant up here, but it was close by, and it was easier than switching it out for the nectar we normally use. I just wasn't bothered. I put in 200 kilos of supercoolant there, and that 200 kilos I actually filled both of those. Or did I put down 4? You know what? Doesn't matter. Those are done. All I got to do now is seal this area back up, and we can start turning this thing on. Well, actually, no. I have to double, triple, and quadruple check everything. Because, yeah, this is not going to be very serviceable. This is going to be a little bit, let's just say if we mess up the start of this, it could be a problem. I was just about to start it up when I realised I'd forgotten the temperature shift plates. I need to put in a temperature shift plate there, and 2 there to finish the build. So I have to break back in somehow without breaking the vacuum seal and without letting that hydrogen gas escape or contaminate any of the other areas, and still pull out all of the debris behind us. Could be tricky. Could be tricky. We're going to try coming in from the bottom and the side. If we take out that door, maybe we can diagonally build those 2. Oh. I was about to find out and you decided to... Okay, I understand. Lunch is important. We all want our lunch. And no. Damn it. Gonna have to figure out another way. Our second attempt is to come through this direction. Ugh, there's always something you forget. I should have triple checked this before I sealed it up. I thought I had, but I was double checking the piping, I was double checking the automation. I never thought about the temperature shift plates, which are really, really important. I got these ones. These 5 absolutely essential because they're the thermium ones. But I forgot about these 2, and I'm pretty sure this won't work without them. We are finally getting in there. Perfect. We're also going to get in to this section through here. In fact, I think I'm going to put in 2 temperature shift plates here, just because we can. Well, we got them all installed. Time to seal up, mop up, and get out of here. We can finally start prepping this thing, or turning it on. We do have to mop up that visco gel before we go. Actually, do we? Now that I think about it, what does visco gel turn into? Converts to naphtha. Right, so the visco gel would just turn into naphtha if we left it here. Actually, no. No. This stuff's kind of expensive. We might as well keep it just in case. But yes, we could theoretically have left it there and not worried. Oh, and in case you're wondering, this is how I'm basically making liquid locks. I grab a bottle of visco gel. I make 100 kilos of it, grab it somewhere, drop it off, and then you can just hit empty. And then once it's empty, it becomes the blob that blocks everything. It's really handy. It makes... the production of liquid locks is so simplified at this point. You can just chuck down a blob wherever you want it. Done. Same with that one, for example. That one's, whatever, 94.6 kilos. I lost somewhere along the way. It falls off edges occasionally. But who cares? As long as you got the main blob, you're good to go. Once that last tile goes in, we're good. Power is connected from down here. This whole thing can be self-powered. It can power itself, but it's going to be a while. We're going to be dumping a lot of power into this until it gets up to speed. So we have our main power spine coming in from over here, and then it's hooked into these 3 transformers. Those 3 transformers are going to plug in to make sure that this thing runs consistently until it gets up to speed. And once it does that, well, we'll be able to run all of these natural gas generators flat out. Well, 16.6 natural gas generators flat out. So it's about 13 kilowatts. It's better than a petroleum boiler, but an awful lot more difficult to build. I still always find these things a little bit inconvenient. They fall into that weird category of a petroleum boiler solves your problems, gives you 10 kilowatts of power. A small sour gas boiler is just far more complicated, and even if it gives you a little bit more power, it's just the amount of materials and stuff you need. Or you can build a giant one, which can process an enormous amount and give you even more power that you'll never need, but that will also take more extra time and resources. So this is sort of like a small, compact one, and it's just... I probably should have made one that did not need to be turned on and offable, but it's just we're running this on plastic, so I want to be able to turn it on and off as necessary. Right now, this thing is heating up. It's got to get this up to an operating temperature of 555 degrees before we even think about putting any naphtha in here. At the same time, this door is engaged, namely because this over here wants to be 200 degrees. And the game is taking a lot longer to save. Might be all the stuff we've got going on in this thing. But anyway, this is a sucking temperature from here. Temperature shift plate injecting into this tile. Steel airlock over here. This whole thing, yep, just getting up to temperature. And then over here we've got another mechanized airlock. That's draining heat out of this area into here to pre-warm the plastic. We'll go more into that later. This is actually kind of unnecessary, but I left it in just for demonstration purposes. We could replace this with a mostly metal block. And then, yeah, what about over here? Oh yes, this is basically generating heat, but it's also generating chill. That chill needs to go over here. And if the chill becomes too much, then this injects a little bit of heat. So this is basically an extra heat source, the tepodizer. And this is going to take probably 8 to 10 cycles before this thing starts, or that gets up to temperature. This is just getting up to about 430. It's not at the 555 it needs to. However, this over here is hitting the minus 181, and it'll go to minus 182 in a second. When it does, this door is going to start kicking in every so often, just sort of feathering the throttle a little bit to like keep that at the correct temperature. Perfect. Now we just gotta wait until this goes up a bit. This area over here is preheated to 159, thanks to all the hydrogen and the metal tiles. This area over here is preheated to 200 degrees, thanks to, well, all the hydrogen and the metal tiles. And, oh, I'm actually getting ready to inject plastic into the system as well. Ooh, finally! Up and running. That didn't take nearly as long as I thought it was going to take. Alright, you. We want to set you to plastic. Done. And no conveyor receptacle because I never plugged you in with conveyor. There you go. And then once that's connected, the plastic will start flowing this direction. Come on. Someone get around here to putting in that conveyor rail. Done. Right, start motoring. Now, this area over here we could have gotten rid of. I'll go back in time and show you some of the previous iterations and how this sort of evolved. But the general plan here is this. It comes down here and gets dumped into this conveyor receptacle. Then this guy, I'll set him to plastic as well. This guy's also going to pick up the plastic. So you are going to be level 1 and you can be level 2. So what happens is it comes down here and this room is hot. 158 degrees-ish, 159. That tends to preheat the plastic. So even if the plastic comes in cold, it should get preheated in here. Then it gets dumped into this thing where it also is going to get preheated. And then it's going to start flowing out. It's going to start flowing out. Okay, where is it? Why is it not flowing? It's disabled by automation grid. Yes, I forgot. I put in an on-off switch. I'm an idiot. Okay. This switch here turns on, which goes into this AND gate. Because the two of them are green, that makes that green. And because the two of those are green, that makes that green. And at the same time, that greenness goes all the way around here and opens this door. Yeah, that door will become important in a bit. But for now, this conveyor rail is spitting out the plastic. The plastic is starting out at about 44 degrees. By the time it leaves this little room, it's up to actually only about 50. It's going to take a little bit of time for that one to get any better. Anyway, down here it's going through all of this area and it's slowly going to start getting heated up. This is going to take a while. So the first runs through are going to be rather slow. And basically it's drawing all this heat from over here. And this guy. Let's give this a cycle or 3 to build up to speed. Right about now we're starting to get up to speed. Well, okay, we're getting up to 150-ish, and then we should see that plastic will melt that's on the bars, and then a new batch will get injected. It needs to hit about 160 degrees. And, come on, nope, still contents is there. Done. Now this is very slow right now. It's going to speed up as the thing as the thing processes and we get counterflow going on. But for now, it's going to be a little bit slow, and we're going to have this down here. The thing is, I want to build up a little bit of a backlog, so this is set to only start pumping once we hit 250 kgs. Before that, we're not going to process anything. So let's skip forward in time a bit until the first batch of Naphtha starts to get processed. Oh, and this is set to 2,239 grams a second. These ones over here are set to 750 grams apiece. And we'll go over why those numbers exist in a bit, but for now, we just want to get this thing started. Here we go. It just did the pumping. And off it goes. It's then going to get broken up into those smaller batches, and then they're going to slide down here, hit this tile, at which point they're going to get heated. And they're going to get flashed into sour gas, basically heating them all the way up. And then that sour gas is going to counterflow over here. Now at the start here, I'm putting in this gas pump, and I basically have it going full tilt down into here. The reason being is, well, methane. You see, these things down here are cold, but they're not freezing it to solid temperatures or liquid temperatures cold. So what happens is this stuff comes down here, and it's not quite hitting the temperatures we require. It's going to take a little bit of time. And when it does, it's immediately going to flash to natural gas. It's going to turn to methane and then immediately flash back to natural gas because it interacts with the hydrosensor or the liquid pump or something. And then normally what happens is a blob of it's going to go back up the tube. Yep, there we go. Causing us all sorts of problems. So for now, once it gets back up there though, it'll float to the top. Natural gas is lighter than sour gas. So that's going to float right back up to the top, and when it does, it's going to get picked up by that gas pump and sent right back down again. Now this will all even out in the end, but we just need to put in the gas pump. I think I had to do this, yeah, I definitely did have to do this on my maximum sized sour gas boiler, because methane just happens. It is going to convert. And I was wondering, why didn't I just put it at the top? And it's because otherwise you have to run the supercoolant a really long distance. What you could do is, say, have this cooling block at the top of your cooling section, and that way any natural gas that happens will basically float to the top of this instead of to the top of this chamber. But then if you do that, all of the cooling from down here, all the cooling this is generating would have to be piped up somewhere. It just made it more complicated. So for now, it's an absolute catastrophic mess, you'll notice. It's just monstrously messy, but that's okay. It's fine. This, oh, 1 second. This hydro sensor is not set to pump anything until it hits above 250 kgs. So there's no rush. We're just going to wait until this sorts itself out. It's probably going to take a cycle or 3. And then once it is, we'll have no more methane forming or no more natural gas forming, because we'll have a nice pool of methane down here. Liquid pump is already down to minus 180-ish. And these temperature shift plates back here, they're minus 179. Once they hit about 180-ish, we should stop seeing any flashing back and forth. Yeah, much better. Now we just got to wait until that natural gas gets up to the top. Once it does, gas pump will pump it down. Finished. I even put in a gas element sensor here. And we're going to set that to, should already be set to sour gas. Yeah. That means if any sour gas is detected in that tile, it'll send an on signal to the automation, and for the next 20 seconds, I want to say, is it 20 or 25? 20 seconds, it will turn that gas pump on. Later on, we'll turn off this gas pump, but I'm going to leave it in here just in case. We could have ways of coming in, getting it in and removing it, but I figure it's better off just to leave it there and not need it than need it and not have it. Yeah, how are we looking? Yeah, that's still going. Gas is still pumping. Liquids are still churning. This thing is still at temp. Oh, you're dipping. Ooh, struggling a little bit there, are you? We may have to turn off the input on this guy. I'd prefer not to. No, never mind, there he is. He's cut back up again. And that is the last piece of natural gas that's escaped. Come on, grab it. Seriously, all you have to do is stay in this tile for a little bit. Like, how is that? At some point, it will catch it. I swear. It's just... Hey, it's finally done. Okay. System is clear of that junk. We could turn off that gas pump, but I think we're fine for now. I'll leave it on for a little bit longer. This has still not hit 250 kgs, though this thing is... Oof. I didn't do a full dry run test on the fully completed design, or like a clean start, as I didn't build it all entirely in debug menu somewhere and check it out. I'm hopeful. Actually, no, it is. It's still holding up. So this should be one that you just turn on and it just works, hopefully, and then it can be turned on and off afterwards. For now, though, we just got to wait for the next stage, which is when this hydro sensor hits 250 kgs. At that point, that liquid methane is going to start getting pumped right back through the system. And it's going to start preheating this area. And I might want to turn off these guys for a second. These are the natural gas generators. I haven't got them hooked up to the power supply yet. But we have plans for this whole area. This is going to be a steam room. And it's going to self-steam. Though that will be a minute. Precisely 70 kilos from now. As far as I'm aware, we could leave that gas pump on. But since it's no longer necessary, I think I'm just going to turn it off, save the energy. Why is it still on? Sorry, natural gas. Yep, my bad. So that's supposed to be detecting natural gas, which is why it was still on. Set it to detecting sour gas. Okay, I won't mop it. Done. Alright, so that's turned off. You should be just about hitting, 250. Alright, so the moment this hit 250, it starts pumping the liquid methane out of there. Now, that liquid methane, once it heats above a certain temperature, turns into natural gas. But we've limited the pipe to 750 grams. You can do it up to a kilo, but we're limited to 750 grams because of just the way the numbers worked out. We'll go over a little bit more on that when we're going through the design phases I went through on all this. But that's counterflowing up through here, and then what it does is, well, that's minus 157 there, and then by the time it gets through here, it's 91 degrees. So it's basically passing through all the sour gas that's coming down here and chilling down, pre-chilling all the sour gas, so it doesn't take as much temperature to chill it. And then once it's finished, it's getting heated up, and because it's hot, it's coming in at 270 degrees, and then it flows through the plastic preheater. So right now, the plastic preheater is pretty slow. It takes a long time for it to melt anything, but right now it's getting dosed with boiling hot methane, or sorry, boiling hot natural gas, and the boiling hot natural gas comes down here and gets dumped into this room. Done. And then, well, the moment it pops out as a liquid, it turns instantly into a gas. And then that's where our natural gas is stored for now. And as you can see, it's speeding up. It's going to speed up now because we're dumping extra heat in here to preheat the plastic. So the plastic's going to start melting faster. And when that starts melting faster, we're going to end up with more naphtha going in here, which means more sour gas is going to get in here faster, which means more methane is going to get pumped, which is going to turn into more natural gas, which is going to preheat the plastic. And the whole thing starts to speed up and speed up and speed up until eventually it's flat out. That, however, will take a few minutes. Once it gets to about 20 kilos of pressure in here, though, we might want to start... Actually, I might wait till it's a little bit higher. I'll wait until some of these gas reservoirs have been maybe filled before I do anything. Just in case. Actually, wait, no, what am I doing? Let's let it ride. I say we turn it on, and let's see what happens. I'm curious to see if we just had to turn this thing on, don't make any changes, don't do any tweaking, will it just run correctly? Oh. Why are you not turning on? Oh, I don't have the automation wire connected. Oh, yeah, there we go. Yeah, so automation wire connected up. That means the natural gas starts getting pumped, which then immediately gets dumped into the natural gas generators. The natural gas generators, well, they drop out polluted water and carbon dioxide. The carbon dioxide we're pumping out and down into the oil biome. Do we need to? Probably not, and something's messed up here. Why aren't you hooked up correctly? You go there, you go there. Ah, you go there. Yeah, it's missing a gas pipe. That'll get fixed in a minute. And then this place is slowly going to get hotter and hotter and hotter. That's quite hot natural gas. It's coming in at about 200 degrees. So 200 degree natural gas going into this room. It's being burned in the natural gas generators. And the natural gas generators, I believe, output stuff. Not quite at the temperature they're at. But wait a minute, where is it? It will be at least 40 C or hotter if the building is hotter. Carbon dioxide, it will be at least 110 C or hotter if the building is hotter. Maybe I should make the carbon dioxide pipes out of radiant as well. Actually, no. If they're 110, we'll leave them. We'll leave them, no point. Why are you overheating? Whoa, 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 whoa. That guy should not be doing anything. Do you have any liquid in you? You have supercoolant. Fine. We're going to have to wait until some steam comes in here, or this thing is going to get damaged. Or... what's the temperature? No, it's 516 degrees. That was silly of me. I should have disabled that thing. I didn't think it'd kick in. I thought it'd stay off. I have disabled auto repair for now. We'll just have to wait until some steam gets there. Ah, there we go. We're starting to get steam already. See, these things are starting to get hotter because this stuff is going through the water and it's 100 degrees. So it's coming in nice and hot. It passes through the wastewater at the bottom and then it goes into the natural gas generators, which they're hot as well. So they're outputting the water hotter and hotter as they get hotter. Soon this will be just a lovely, delicious steam room. Ooh. You know what? Give me a temperature shift plate. Make that out of diamond. Put that sucker right there and there. Want to make sure that this visco gel does not start doing anything wonky when liquid goes near it. That's why this is triple liquid lock. We got a blob there, and a third blob there. There should be no chance of this breaking open, but Randy finds a way. Looking back at the boiler, oh, something's gone wrong. Damn it. Okay, so maybe I should have not turned this on quite so quickly. Alright, so this is filled up. We're going to have to turn this sucker off. It would have shut off automatically once this hits 100 kilos of pressure, which it has. So the moment it shut that off, it should stop that pumping. It has. Okay, so the system is off. Why is more naphtha being pumped? No. Okay. This is why we put in safety features. This is all going to turn into sour gas rather rapidly. Now, I never had this happen in testing. So what I need to do is see how long I need to leave on this filter gate. This filter gate means... No, let's make it 200 seconds. This filter gate means the whole system won't turn back on until after this liquid naphtha has been flashed. The automation here basically says if it goes above 100 kilos of naphtha in here, basically shut off. Shut this system off. It just sends an off signal here, and all of these things have to be all green or it won't stay on. There, it's flashed. So this is sent a signal up going, hey, there's no more naphtha in here. However, there's this buffer gate here, and it says wait 200 seconds. The reason we want to wait is we need this to get back up to 555. Once it's back up at 555, we should be clear to start the system again. Huh. It did not need the 200 seconds. Okay, so let's make it 100. Oh, we reset the timer. It's fine. Alright then, once that gets back up to speed, we'll then be able to start dumping the natural gas in here again. Alright, Q has been given. Plastic has started flowing again. This here is... Oh, whoa. Why haven't you started pumping? You should already be pumping. Oh, it is. Perfect. How are you looking? Yeah, temperature's holding steady. That's flashing to sour gas. Sour gas is going all the way around. Counterflow is doing its job. Right, I'll keep an eye on you. Don't do anything sloppy. That is looking beauteous. It's all flowing nicely, and there's the odd break, like there was a little break there, but by and large, it's almost a solid stream now. How are you looking on the hydro sensor? Yeah, it's about the 250. How are you looking? Oh, you actually went below spec. Oop, we're going to have a few breaks here and there until it evens out. And how are you looking? Still at 255. And over here, this natural gas generator is at 102.4 degrees, 0.5, 0.6, going up and up and up. Just got to get up to that point where it causes all the polluted water below it to evaporate before it floods so much that it can't work anymore. Which should be fine, probably. Something, somewhere, is flashing to water. Give me gas. Okay, so some of them are starting to turn into steam. Sorry, when I say flashing to water, I mean the polluted water is turning into steam somewhere. So, which one of you is too hot? You're at 113, you're 116, you're 128. So the liquid coming out of you is probably pretty hot. Perfect. Now, as the steam pressure starts to rise in there, it should mean that all of the natural gas generators will go above about 125, and then it's just a constant after that. Constant steam. You're at 550. I'm keeping an eye on this guy, but he hasn't messed up again. I mean, I know I shouldn't be eyeballing constantly, but if you mess up one time, you kind of gotta keep an eye on him. Okay, everything should be flowing smoothly. Yep, the preheaters are doing their job. There, see, there's a gap there, so it's not actually up to full speed yet. There's still the odd break in the pipe. Say another 2 cycles or so, and I think it should be completely done. We just gotta wait until this gets up to temp as well, so that all of this polluted water down here starts turning into steam. That's a lot of polluted water down there. I might want to mop up some of it just to... Nah, let it go. We'll let it ride for another couple of cycles and see what happens. No, what the... The steam turbine has kicked in. Seriously? Okay. I suppose it actually is hot enough. You know what? No. Turn off. We're going to leave you off for now. There's no need for you to be kicking in just yet. We'll wait until all the polluted water in here has been turned to steam. There's still like 36 kgs of polluted water down here. Once the polluted water's gone, then we'll turn on the steam turbine. Looking here, we can actually see the polluted water evaporating, turning into steam slowly but surely. Yeah, I believe it's the natural gas reservoir has finally broken them. And it's basically, it's so slow because all of the water over here is pouring to this end. And I'm going to pour to this end, it hits the gas reservoir and starts flashing to steam. How much steam we got in the room? 6 kilos per ton. I'll wait until it's up a little bit more before I turn on the atmo sensor. We're going to need to have somebody to strain some of that out. We're going to keep about 20 kilos of pressure in here to keep the whole thing going, but then the remaining water is going to have to be output somewhere else. And this over here is... Yep. Oh, was that a break? Yeah, you can see there, cut out for a minute. Still needs a little bit more warm-up time. Oh, actually, yeah, that's something I should do, is plug in the power for all these guys. You, give me a heavy wire conductive wire. Which way am I supposed to plug? You know what? Doesn't make a difference. You can go that direction. So that's that one in, and that one in. That means we can sever these power wires here. You can be severed, you can be severed, you can be severed. So the whole thing should now be self-powered. Should have done that a while ago. Over here, I haven't plugged in the batteries or any of these transformers up here. These are basically... This is leftover space, and we're using that basically as a plug socket. These are self-cooled transformers. They'll be in here in this area so they can't overheat. We've also got a bit of a smart battery that we haven't plugged in yet so that we can turn these on and off as we need them. All right. And I mean, I like to think that this thing looks reasonably sane. Like, it's got a nice shape to it. All the space is used. It's not too ridiculous. And it seems like the actions of someone who kind of knew what they were doing, almost. Almost. But yeah, a lot of this was just improvised on the fly. I think I can go back and show you why half of the stuff exists. It's probably easier than trying to explain it as it is now. You should see all the things that failed to make you understand why it ended up the way it is now. Looking back a bit, this was, I think, the original design we tried. Then we went on to this one. And this was my third attempt. This one here actually has a lot of the things that would become standard a little bit later on. Basically, we were having the plastic come in here. The plastic was metered out to 2.5 kgs per second, and then it would come in here, go around and start rotating. Problem was, we ended up with Naphtha spawning on this side, which is a problem. We didn't want the Naphtha spawning in there because that's where the gas pumps were supposed to go. Oh, and these things here are just storages, they were for testing. We'd store the natural gas in there, just, so you can ignore those pieces. And then I did a little bit of testing here, and it turns out if you run plastic on a conveyor rail down a metal tiles, it always pops out to the left-hand side, unless you block it. So this meant we had to take this design and basically mirror it so that the gas pumps were on the right-hand side, and the whole thing was mirrored. So we ended up with this design, which looks very similar to what you've got. We still got the 2.5 kilo limiting, we still got this stuff coming in here, and we started adding in oxygen atmosphere, not just to these sections, so that we could get better temperature transfer. In fact, a lot of the basics is here. It just took a little bit of tweaking. Now, this worked-ish, but it wasn't great. The problem is, you can see here, these are all 2.5 kilos of plastic, and the problem is they're not melting as fast as they get down. You'll see that there's a stutter in it. So even if you left this on fully, we weren't able to melt the 2.5 kilos of plastic returns in Naphtha, which meant we weren't able to process this much Naphtha per second, which meant the whole thing was just not working at speed. So modifications needed to be made. Though over here you can already see we have the 750 grams flow control. We have this hydro sensor set to 250 kgs. This is set to 555. This is set to minus 170. And we do have a thermo sensor buried in that ice there that's set to minus 182. So most of these settings were already confirmed. This one here above 20 kgs. And we already had the gas pump in here. When we started making this, yeah, we encountered the problem with the methane. In fact, that's why the pipes look a bit wonky. There was actually a tile there originally before we ripped it out. That actually carries over into the later designs just a little bit. This is the next stage of the design. The biggest change is this section over here. This used to be just sealed off with blocks. But what we did was we started preheating the plastic. The plastic I was getting in, I wanted to make sure it wasn't too hot. We're on a cold map. Some of the plastic we're going to getting in is going to be pretty chill. It's not going to be very hot plastic. And if we start off at a lower temperature than the plastic we're using, that would be a problem. So I wanted to use colder plastic. That's why this stuff is 26 degrees-ish. So what happens here is I was trying to drop this stuff down, have it wait on a weight plate, and then have this entire area heated up to about, 150 degrees. Plastic melts at 159 point whatever. So get the plastic preheated and maybe put a ton of plastic on here or a couple of tons so that the stuff is preheated and it'll be 100 plus degrees. Was not very efficient. However, one of the accidents I did right here is I removed the limiter, as in the limiter that was setting it to 2.5 kilos on the wire, which was actually a great thing, because what happened was, with the preheating and all of everything that was going on and the pumping of gas and all this stuff in here, it was actually working out that this thing was running almost flat out. Not quite, but almost. This here, though, was not quite perfect yet, but most of the other things have all the other design quirks have already been ironed out. Oh, see this block here? absolutely unnecessary. I could actually get rid of that airflow tile. I don't know why it's there, but once it was in, I'm like, I'm not removing it. This is finally starting to look exactly like it needs to be. A couple of additions. We've put in a mechanized airlock here. Over here, we've put in the conveyor receptacle. Reason being, it limits it to a ton. And you'll see here, it actually heats up the plastic quite nicely. That is a steel conveyor receptacle and a steel conveyor loader. We got rid of the blob of liquid. It wasn't really necessary, and we filled the whole room with hydrogen to increase temperature transfer. Now, the thing is, originally I was meaning this to be an accessible area where a duplicate could come in and drop off the resources, but then I realized it was probably easier to just have it conveyored in from a distance. Especially around this time, I was thinking we were going to add power to this. And since on our map, this is going to be on the left-hand side, or we were on the map the map we're playing, when we installed this, we were going to have the gas pumps on this side. It was more than likely that I was going to put the power brick on this side, and I wanted the power brick to be accessible, which meant this was going to be going on the left side of the map, which meant all of the plastic would be coming in from this side, more than likely. Now, the reason we put in this right here was so we could start putting in some flow control. You see, we have a power switch over here, which can basically turn off the whole system. Like right now, it's running flat out. Works like a charm. We do have a temperature sensor here to make sure that the temperature stays right, but there's a few negatives. I'll just cover some of the negatives. One, if we end up with too much plastic melting, right now it's at 480 kilos, this will eventually fill up, and this will start filling all the way back up the system. That would not be great. So what we're doing here is we do have to take care of that at some point. But for now, what we want to do is find a way to switch this on and off where it still works. So we're going to flick that switch off, and what that does is send a signal over here and tells this guy, hey, stop loading up more plastic. It'll switch off that. At the same time, it goes to these buffer gates. These buffer gates take 400 seconds to process. And after 400 seconds, they will close this door, and at the same time, they will shut off this liquid pump. And once both of those are done, actually, let's fast forward this a little bit with super speed. Only available in debug mode. We're about halfway through here, but you'll notice there's still plastic left on this line. We just got to keep an eye on that door. And by the time the plastic runs out, and by the time the door closes, it should be almost identical timings. And not quite. And how is our automation looking? Okay, so the plastic is just finished, and then this door closes. Reasons why this is important. What would happen is if we switch this off, without actually having a blocking thing here, what happens is all of this sour gas keeps flowing. And it keeps coming over here and it needs to be cooled. And because it needs to be cooled, it keeps turning on the thermal aquatuner, and the aquatuner keeps cooling it down. Problem is, there's nothing bleeding heat out anymore. Since there's no other naphtha or plastic being injected into the system, this thing would just keep generating heat, causing it to go over above 600-700 degrees, that type of stuff, and it gets up so hot it causes problems and breaks the system. So putting in the door stops all of that from getting in there. That's actually a perfect vacuum there, because everything behind this has been turned into liquid methane. So that was one of the first safety features we put in, or one of the first features to make sure that we could turn off the system and turn it back on again. Then what we can do is just flip the switch again, and boom, you see the plastic starts going along the wire, but at the same time, methane starts flowing too. Done. Whole system kicks back into gear. It will stutter a little bit at the start until the plastic catches back up, because all of this plastic hasn't been preheated, but we couldn't leave the plastic in here. If we left the plastic in here, it would overflow the system. Anyway, that was just some of the steps. This is when we installed the hydro sensor. The hydro sensor here was to make sure that if this overflowed with naphtha, as in this thing backed up because we hadn't been generating enough heat, which happened one time during testing. It never happened after I installed it, though maybe it happened, I don't know. You know what, doesn't make a difference. What does it just checks if the naphtha keeps building up in here because there's not enough heat to flash it, in which case it will send an off signal, and that off signal could go over, where is it? It goes over here and shuts off this system. I do actually need to make a change to this. What I need to do is not actually turn off the counterflow. Oh, I think I need to turn off just the plastic input, or maybe just turn off the liquid pump. If it stops the liquid pump, that should be all that's necessary. Yeah, I might have to break back in and make some changes on the current design. You know what? Not going to worry about it. But at this point, we got most of the safety features installed, and the whole thing was flowing, well, quite nicely. However, there was one thing that had been pointed out to me in the comments. If you take 1 ton of, or 1,000 kilos of sour gas and you freeze it down, you'll end up with 670 kilos of methane and 330 kilos of sulfur. That's the actual full transfer rate. I thought it was 66.666 and 33.333. No, this is the actual rate. So what that meant was I had to change the input settings on this to 2,239. It's not quite perfect, but assuming you're switching it on and off once every few thousand cycles, this thing should have no problems, even if you're putting in just a little bit too much liquid. Done. And that was just all the little tweaks that went into making it just work, and that's why it looks this way, and that's why there's that stupid amount of automation. Oh, and another thing, see these liquid vents? Let's just take out, say, half of them. Yeah, that'll be fine. Check the temperature down here, we're at 255. Let's speed up time a little bit. And watch as the temperature just plummets. Those liquid vents are entirely necessary to keep up the counterflow heat exchanger. Otherwise, the whole thing overloads and stops running in short order. Yeah, see the temperature just plummets. So every single one of those is absolutely necessary. There's like not a lot of leeway in some of these things. This was my first attempt at sticking on some power onto it. I was just trying to get an eyeball for it and whether or not I should put in power or whether I should stick a steam turbine on top. Initially, I was actually just going to pump out the liquids, but then I started thinking we could maybe squeeze this in a little bit nicer. The initial power brick looked like this with these top two tiles wasted. I was going to use that as a maintenance corridor. And then over here, this was meant to be passively cooled, as in the heat generated by this was supposed to passively cool down the steam turbine. Didn't work out. Once you ran it long enough, the steam turbine started overheating and the whole thing fell out of sync. And we already had the idea of putting through the radiant pipes and getting the whole system running that way. It just needed cooling, which meant we needed to put in an aqua tuner, and I hadn't put in any gas storage at this point, and we needed gas storage if we wanted this thing to be able to run more than intermittently. As you can see, that's maxed out at 100 degrees. Passive cooling just could not do the job, unfortunately. And this over here, yep, the great thing is this thing was just churning away quite nice in the corner. We didn't have to do anything. This is starting to look more like the finished product now. We've moved the steam turbine over here. We've decided that this is going to be a, well, basically, if you've got a 2-tile high corridor, it's either transformers or batteries. It's one or the other. We have squeezed in everything here, but I haven't put in any sort of maintenance corridor or anything like that, so this is still just more of a rough print. However, we already have the idea for this, where this thing here has to stay at 20 kgs, and if it goes above 20 kgs, it sends an automation signal up here, and the output water gets siphoned out. I did make a brief attempt here to try and cool this thing down using a thermal regulator, like the gas-powered cooling units as opposed to the thermal aquatuner, just to try something different. It did not generate enough cooling, even running hydrogen, to cool down the steam turbine. So that's why we switched back to the thermal aquatuner, and that's why that gas piping is there. Messy times. Not quite the finished product just yet, but definitely closer. We've even got the idea for this bead liquid lock. That's actually liquid naphtha there, 2 kilos of naphtha at each of those squares. Means we've got a vacuum seal all the way through, meaning heat can't transfer. And duplicants can come in here and walk down. And they have full access to the whole area, and we've already got in the large power transformers. Aquatuners already in place. Yeah, pretty much done-ish. Then I consider putting the gas reservoirs in their own sort of broken off area in storage, and then having the gas come in. Problem was, it just wasn't really viable. We were still left with all of this dead space up here. So I figured if we moved the gas reservoirs in here, we could extend on these mesh tiles and put in more large power transformers. This thing can handle about 13 kilowatts of power. So I figured 2, 4, 6, 8. This could only output 8. We needed to be able to squeeze in a few more large power transformers, so probably better to move these in. Also, that's how we came up with this idea for the power outlay of this guy. Instead of having this power just wasted or having to run a heavy watt joint plate in there, all this guy does is this power comes out here, runs into this heavy transformer, and then that power is dumped onto the grid. As in, we're using the power transformer not to take power off a main wire, we're taking a smaller wire and feeding it onto a big wire. And it also runs the liquid shutoff. Why not? It just seemed convenient at the time. But yeah, once I'd put these here, I realized it was just going to be a waste of space, so I needed some way to, and putting in more large power transformers just seemed to fit more with what we would need. Initially, I had tried putting the gas reservoirs on the end. The problem was, it was really inconvenient. The problem is you'd have to run the gas over there first and then bring it back out. It's just, we wanted to store up the gas and have the gas ready to go when we needed it. So what happens here is the gas is stored up in these tanks, then that gas is fed all the way along into all of these, and this is the last natural gas generator. The reason this one is here is because there's not enough gas to actually run this one. In fact, if you'll notice, both of these have bridges set onto them, so both of them are pumping the last gasps of gas in here, namely because this is 1 kilo and this is half a kilo, and both of them can run like a set number of natural gas generators, but with a little bit left over. So all that little bit gets fed into this guy at the end. And then what I wanted was, I wanted some way to turn this on and off, as in we can turn this on, use it as much as we want, get as much natural gas, but then what will happen is once the gas tanks are full, the system would shut off. Then once the gas tanks start to empty, the system would kick back in again, and the gas tanks, until it ran back up to full speed, the gas tank should have enough gas to keep the whole system running. So that means we needed to test it. So this here is the whole system filled up with a backlog of natural gas going all the way back to here. System's been disabled, namely because this thing is set to say, hey, if we go above the high threshold, send a red signal. And this over here is an AND gate. So long as both of them are sending red signals, what happens is it sends an off signal to this AND gate. And so long as both of them are, well, so long as one of them is off, that means it sends a red signal, which goes into this AND gate, which also sends a red signal. Damn it, how many off signals are there? Okay, so this can send an off signal if too much naphtha ends up in the system. Oh, wait, no, that's the wrong one. This can send it on or off signal. That's basically how to turn on and off the whole thing. That's just basically our master switch, in case you ever want to turn it off. This can send it on and off signal if there is not enough natural gas signal. If there's too much natural gas, it'll tell it to turn off. And this, if we end up with too much naphtha down here, it'll turn it off. Though now that I'm thinking about it, that's a huge mistake. I can't have that feeding in because otherwise there's no way to turn it back on again, and we need some way of draining the system. Yeah, I'm going to have to make some modifications on that one. Mistakes were made. However, once we flick this switch again, what that should do is start all the natural gas generators. That means the natural gas starts to flow. Right, I think that should be switching to green any second now. Yeah, first one's gone green. Second one should go green in a second. Oh, I've done this wrong. This guy's set to 9590. This guy should be set to 9592.5 if possible. Actually, no, we can't do that. Okay, so you can be set to 90, but that means this guy needs to be set to 85. Reason being, that means they should both switch at the same time. Yeah, there we go. And once that switch happened and they turned the whole system back on, the plastic starts to flow. You can see that this plastic here is really starting to heat up, like especially near the top, like top to bottom. So what happens is it's like this whole batch back here is preheating, and while it can only melt the bottom bits, well, it theoretically could melt the higher up bits. It's more likely to melt the bottom bits. And then what happens is the next batch in is so preheated that it melts an awful lot faster, which is why melting them in 20 kg batches as opposed to 2.5 is so much more efficient. You see, look, and the next roll goes through, and now we're back to a whole bunch of fresh plastic that's going to take a while to get up to temp. And that's it. So, system's going to take a while to kick back in, but while it's slowly kicking back in, even if we need all the power, right now, we got the whole thing switched on. Even if we do need all the power right now, this thing is going to be well up to speed before it could drain any of these. Namely because we've got one whole gas tank here feeding these 6-ish, 5.5, let's say. And we've got two gas tanks feeding the bottom 11.5-ish ones. That way, these things won't even be half empty, or should not be more than half empty by the time this gets up to full speed, where we're seeing nothing but pure methane flowing down the line. So there's still the odd tiny break here and there. Wait, no, I think we're back up to full speed. Oh no, there it is. See, tiny break. However, we're still getting enough natural gas out and pumping it in that it's just these things will never go down far enough. So the system's now almost completely stable, and it can provide us the full wattage we need. So it's basically a sour gas boiler you can turn on and off, that runs on plastic, is reasonably stable, has a bunch of built-in safety features to make sure it doesn't break, or if it does break, you can at least recover from it. However, it's non-serviceable, but it is quite compact, and it fits into a lovely, that is 16 by 51 tiles. Well, actually, to there, 51. The reason I squished it back a bit was, well, this was 2 tiles wide, so instead I moved this whole doorway over 1 tile, which is why the finished design looks a little bit different. Or should I say, this was the template design. This is the slightly tweaked finished design. For the finishing tweak, I moved, the battery back here as opposed to over there, namely because I wanted the power wires to be able to get out of the base. If we put the battery in front of it, what happened was the battery basically blocked this one from getting out because it couldn't get past this slot, namely because you have to put one of these down here. It was a whole mess. So instead I moved the battery over to the side, and I also put the liquid shut-off over here inside, on the grounds that it was probably just closer, and it fit in because we had an extra 2 tiles of space. A couple of extra temperature shift plates here. We switched over to visco gel instead of using the Naphtha. That means we were able to get rid of the heavy watt joint plate that was there, and I considered making it another 2 here, but I figured I'd just leave this here. It was simpler, and it makes me feel a little bit more comfortable knowing that those 2 are there with a much harder way for it to get through. That visco stuff, it's good, it just, I don't always trust it. We also moved our power switch over here from outside. This is what allows us to turn on and off the entire natural gas generator array. We still haven't plugged this into our main grid, by the way. And yeah, I really need to fix the automation on this. Namely because in the testing, this pressure never got too high. But I'm pretty sure we're going to see this go up a lot higher because the plastic we're feeding into this is about 20 degrees hotter. Or like, oof. Yeah, it's hotter than the stuff we were getting, or we were using. So that means more plastic is going to melt faster, which means this is going to go up a little bit more. So I'll have to fix the automation on that. But barring that, that's how we ended up with this design. I mean, it looks a little bit cluttered and busy at times. I did some changes to the piping again. You can't help yourself. Once you start, you can't stop. There's always little tweaks here and there to be made. And the automation is an absolute nightmare. And the amount of settings is ridiculous that you have to remember. 750, 750. I'll attach the save. You can play around with it if you want to have a look at the numbers. 239. Oh, you gotta don't forget the hydro sensor. There's also a thermal sensor in there. Liquid pipe thermal sensor, hydro sensor, gas element sensor, thermal sensor, 2 hydro sensors, another liquid valve, a thermal sensor, and atmo sensor. There is just, this is probably the most automation I've ever had to cram into something because you need to be able to turn it on and off and it needs to be sustainable. It just, no. Remind me never to do something that stupid again. Just make them one of those, turn them on, leave them on, and never look at them again. Those things are the simplest. Oh, and the reason we put all of these on top of heavy watt conductive joint plates, what I initially was planning on doing was I was going to put a blob of visco gel or Naphtha on top of the tiles so we could plug in the large power transformers early to power the whole system, and then that would act as a conductor, having little blobs of liquid there, which meant that things wouldn't overheat. But instead, I just went with plugging them into underneath. I figured it might take a really long time to get this up to speed, and during that time, those things might overheat. So why complicate things? Just plug in the power from the outside. Who cares? So that's why those heavy watt joint plates were there. And yes, I am miles over time again. It took ages. I should have had this out earlier. I had a design that worked. It's just you keep tweaking things and you want to make them right, because I mean that's the thing. You'll make these things once, and then if you ever need to make them again, you can just come back and look at them and go, oh yeah, that's how I did it, and then you can just rip off the design and use it. Anyway, save game is attached. I'm going to cut this out here. I hope you enjoyed it. Good luck.